All right, for this project, we're working with Ohm's law, and we're going to be installing some light bulbs in a circuit, both in series and parallel. First of all, Ohm's law describes the relationship between voltage, current, and resistance. The equation is written as voltage equals I times R. And those can be flipped around. I equals voltage divided by R, or R equals voltage divided by I. V stands for voltage, I is current, R is resistance. And along with this, we are using the power law, which is P equals I times voltage. And again, that can be reorganized to power equals I squared times resistance, or power equals voltage squared divided by resistance. We'll be using these equations throughout our project here. First of all, what is a circuit? A circuit is considered completed when there is a closed loop that allows current to flow. Components include a power source, a conductive path, like a wire, a load, like a light bulb, or a closed switch. Over here in this little image, we've got our power source. We've got a conductive path connecting from the positive to the negative terminals. And we have our load, the light bulb. And in this case, we have an open switch, so this isn't a completed circuit, but we have, once this is closed, we have a completed circuit that would allow the electrons to flow from negative to positive. First, we'll start with the in-series circuit. A circuit in series is one where all the components are connected in a single path. In series, the current is the same throughout all components. However, the voltage is divided among them. So from our assignment, we've got, this is an in-series circuit here. 9-volt supply with a 10, 20, and 30 ohm light bulb. So these will all have the same current traveling through them, but the voltage from each of these light bulbs will be different. So we can do the math with the equations that we had at the beginning. Current equals I equals voltage divided by resistance. And in an in-series circuit, you add all of the resistors together, 10, 20, and 30, giving us 60 full ohms, and you divide that by the voltage that is being provided by the battery, which gives us a current of 0.15 amps. The voltage is voltage equals I times R. So we take 10 ohms, the 10 ohms here for our resistance, times the 15 amps in the current, and that gives us 1.5 volts. For the 20 ohms, we got 3 volts, and for 30 ohms, we have 4.5 volts. To calculate the power, we'll use the resistance. P equals I squared times resistance. I'm sorry, I meant current, not resistance. So for the 10 ohm, it's 0.15 squared times 10. That equals 0.225 watts. For 20 ohms, we got 4.45 watts. And for 30 ohms, we have 0.675 watts. What this tells us is that the brightest bulb in an in-series circuit should be the 30 ohm bulb. I recorded a video to demonstrate this. So the first thing we're going to see once this switch is closed, completing the circuit, is the brightness of each of these lights. You can see 10 has a very small brightness, middle brightness, and then 30 ohms is the brightest, like we predicted. The current throughout is 0.15. And as we're seeing now, no matter where we put the ammeter, the current is always 0.15. Voltage is different per light bulb. For the 10 ohm, it's 1.5. For the 20 ohm, it's 3 volts. And for the 30 ohm, we are at 4.5 volts. Important thing to note here is if you add all those voltages together from the 10, 20, and 30 ohm light bulbs, all of the voltages add up to 9 volts. In contrast to in-series circuits, we have in parallel, which kind of flips the results upside down. A circuit in parallel is one where each component is connected in separate branches. In parallel, voltage is the same throughout all the components. However, current is split between the branches. So we have our little diagram here again. Since all of the light bulbs are connected independently to the battery's power source, all of them receive 9 volts. However, the currents between each of these will be different. So in parallel, finding the current, we take the it's current equals volts divided by resistance. So for the 10 ohm light, we have 9 volts divided by 10 gives us 0.9 amps. For 20 ohms, we have 0.45 amps, and for 30 ohms, we have 0.3 amps, totaling a current of 1.65 amps. For the voltage, as we discussed, in parallel, each bulb receives the full 9 volts from the power source. So 9 volts here, 9 volts there, and 9 volts there. And then to calculate the power, we can use power equals volts squared divided by resistance. So we have, for the 10 ohm, we have 9 squared divided by 10 equals 8.1 watts. For the 20 ohm light, we have 4.05 watts. And for the 30 ohm watt, we have 2.7 watts. This information here again tells us that the brightest light in parallel should be the 10 ohm light bulb. We'll watch a video of me setting that up real quick and run through it. Okay, so once this closes, our prediction was 10 would be the brightest, and we can see that that's the case. It's also the case that each of these light bulbs are shining way brighter than any of them were in series. We can see here we got 1.65 amps, which is what our math told us. Down here, everything should be 1.65 amps, and then each of the individual lights have a different current flowing through them. 0.30 for the 30 ohm, 0.45 for the 20 ohm, and 0.90 for the 10 ohm. And again, each of the different currents flowing through these added together will give us this 1.65 amps. And then, as we discussed, in parallel, all of the lights should receive the same voltage of 9 volts from our power source. And as we can see here, that is the case. So in conclusion, in series, the bulb with the highest resistance is the brightest. In parallel, the bulb with the lowest resistance is the brightest. Brightness is determined by power, which depends on both current and voltage. And all of the bulbs in this simulation did follow Ohm's law.